Hello and welcome to Module 9 video on Thermodynamics II. Today's video is about adiabatic flame temperature. The adiabatic flame temperature, or the adiabatic combustion temperature, is basically the maximum temperature that you can reach during combustion. So of course in Module 9 we're interested in combustion. So for a given combination of fuel and oxidizer at a given initial temperature and pressure, if you assume that none of the heat is released during that combustion, then all of the heat of combustion is used to heat up those combustion products, and so therefore that's the highest temperature that we're going to have in the process. So that's the definition of adiabatic flame temperature. In order to understand how that works, let's apply the conservation of energy to a typical combustion process, one that's going to model this adiabatic flame temperature idea. So applying the conservation of energy to a combustion process. So we'll start off by sketching typical open combustion chamber where some oxidizer and some fuel are mixed together, and let's assume that the chamber is very well insulated so that there is no heat out of the chamber at any point. Of course, there is no shaft work being done in this process. So our oxidizer comes in at state 1, or fuel comes in, let's say, at the same temperature and pressure to keep things simple. And the combustion products are exiting at 2. And of course, the combustion products are now at a different temperature than the fuel and the oxidizer. And that temperature, T sub P, that's what we're after. That's going to be the adiabatic flame temperature. Okay, the temperature of the product, assuming no heat is released. So let's apply the energy equation to this figure. Of course, we could start from scratch with our old faithful Reynolds transport theorem form of the energy equation, but you guys are becoming experts at this now, so we'll cut through the chase and get straight to the final form that we would get if we did that, which is, there's no transient term. All we have is convective terms, one inlet, one outlet. So that means that the mass flow rate of the products times the enthalpy of the products has got to be minus the mass flow rate of the reactants times the enthalpy of the reactants. It's got to be equal to the total rate at which heat is added minus the rate at which work is done, which in this case is 0. So voila, that's it. The mass flow rate of the products times the enthalpy of the products must be equal to the mass flow rate of the reactant times their enthalpy. Typically, though, we're going to put that on a molar basis for this chemical analysis of the combustion process, and that's really where the adiabatic flame temperature equation comes from. So unlike the mass flow rate point here, we're going to look at the number of kilomoles of fuel that we have there times the enthalpy of the products on a per kilomole of fuel basis minus the enthalpy of the reactant on a kilomole per fuel basis. All that equal to 0. That should be an equivalent form here for what we're talking about. So the molar enthalpy of those products is going to be found with respect to a reference state, unlike a lot of the things that we've done before where the enthalpy was given with respect to the 0 state, temperature equal to 0. Here the reference state is typically taken as 25 degrees Celsius and 1 atmosphere, and it's denoted H sub F naught with a bar on top to tell us that it's on a mole basis. That's the enthalpy of formation. And the enthalpy of formation is arbitrarily given the value of 0 at that temperature, at the reference state, for substances that are stable at the reference state. For example, the enthalpy of formation of molecular oxygen, O2, and of molecular nitrogen, N2, are both going to be 0 kilojoules per k mole as they're found in their natural state in the atmosphere. Other products, for example, CO2 and water, which are typical products of a chemical process, are going to have a different enthalpy even at that reference state. So let's keep that in mind for later. But for the stables, a few stable compounds, that's going to be it. Then the total enthalpy at any other temperature and pressure is going to be that enthalpy of formation plus the difference in enthalpy as we move away from that reference state. And that's the normal way in which we'll describe the molar enthalpy of reactants and products of combustion processes. So substituting that back into the equation that we had before on a molar basis, that is going to mean that the sum of the, well, okay, actually let's go back to that equation that we had before there. Oops, I think it's not really an equation here. I forgot to put the equals 0 bit there, didn't I? Let's fix that. Yeah, and in fact, instead of specifically writing it in terms of NF, the number of moles of fuel, we're going to look at the number of moles of products per mole of fuel times the enthalpy of the products per mole of products, and so therefore that's going to be the same as giving us the enthalpy of the products per mole of fuel, which is kind of what we're after. And similarly for the reactants. So that's really the proper way of expressing equation 1 here, which is the molar form of our energy equation results. And now we're going to substitute that back with the form of the molar enthalpy for the products and reactants in terms of the enthalpy of formation and the change in enthalpy as we've just talked about. And that's going to give us the sum over all the products of the enthalpies of formation plus the change in enthalpies on both the reactant and product side. Now, the one thing we don't know is the final temperature of the products, and so that's going to be that delta H bar of the product term. So we're going to isolate that on our left-hand side and put everything else on the right-hand side. Let's finish that off. And that's going to be our key equation. We're going to box that up now because the right-hand side for a given combustion process is going to be completely determined by the temperature at which we introduce the reactants in the combustion chamber, which is known, and of course the enthalpy of formations, which is at a known state as well. So everything is known on the right hand side for the given reaction. The only thing that we don't know is on the left hand side the temperature at which this change in enthalpy takes place. So we're going to isolate that guy over there and call this whole thing equation 2. And that's going to be our main equation to figure out the adiabatic flame temperature. Let's call it T sub AD for adiabatic. Point is, though, that the left-hand side is implicit in that TAD, in that adiabatic flame temperature, meaning that the TAD appears in a whole bunch of terms, as many terms as we have products of combustion. So typically we're going to have to solve that iteratively in order to figure out what T sub 80 is, given that we know everything on the right-hand side, right? So we're going to change that TAD and we're going to get different total enthalpy on the left-hand side. Does it match the right-hand side? Yes, we're done. No, let's keep going. While we do this, let's highlight a few things here that are important. If we're dealing with ideal gases, not perfect because things can change with temperature here, but the enthalpies, the change in enthalpies are going to be functions of temperature only, and we don't need to track the pressure. That's going to be kind of nice. The enthalpies of formation of the products and the reactants on the right-hand side might be hard to get for some combustion process that we have, and an relatively easier way to do this whole process to figure out the right-hand side is to use what's known as the lower heating value, QLHV, of the fuels that we're dealing with. which tells us how much energy is released per unit mass of fuel burnt. And that's a very good approximation for the right-hand side of that equation. And in practical terms, we often use this. Next, we'll look at an example of how this is used to find the adiabatic flame temperature. And we're going to look at that in a different video.